And that is going to be the focus here now. Okay, so I want to take you back to the what we have been doing, okay, on the challenger data, okay, and of course, what you see here is a simple logistic regression model, okay, and you know the y cap here is the expected probability of the characteristics of interest, okay. So if you want to look at the code, okay, if you want to run what we did the other time in R on the where we use the temperature and the O-ring, either damage or not, okay, this is what we're going to write. This is going to be the code, okay. And there's something I want you to see in the output of a logistic regression. I want you to take note of that, okay. In the output of logistic regression, we have estimate. We also have estimate in the output of linear regression. We have standard error. We also have standard error in the output of linear regression too. But you know what? Look at here. This is a z-value, okay? In a linear regression, what we normally have here is t-value. I'm going to say that again. In a linear regression, what we normally have right here is not a z-value, but a t-value, okay? But in a logistic regression, it is not a t-value, it's a z-value, okay? So please take note of that. Then if you look at the p-value, okay, it's actually going to be the p-value associated with a z-value, okay? And in the case of linear regression, it has to be a probability value associated with a t-value, okay? So please take note of that, okay? They are not the same, okay? So, of course, this is my beta naught, this is my beta 1 based on what I have here. And of course, this is how I can actually write the model in terms of probability value, okay? You know, like I said, we can write logistic regression model in 3 ways, okay? It's either you write it in terms of odd ratio, or you write it in terms of log of odd ratio, or you write it in probability value, okay? So this is a way to write that in probability value, okay, in probability, okay, so you're actually going to put the beta naught and the beta 1, okay, of course, take a look at what I showed you here the other time. This is a model, okay, this is where you want to write it in expected probability value of the characteristics of interest. All what you just need to do is to plug in the value of beta naught and the value of beta 1 into the model. Okay, recall in linear regression, how are the models coefficient estimated? Okay, I told you in linear regression that we just did, the model parameters, the beta naught and the beta 1, they are actually estimated using the method of least square, okay? And that's what I'm trying to show you right here, where we're actually going to be looking for the best line of fit, okay? So, which means you remember in the linear regression model, if we want to estimate the parameters in the linear regression model, we're actually going to apply the least square method. And the essence of applying a least square method is because the least square method can actually minimize the residual sum of square. But in the case of logistic regression, the question now is, how are the model coefficient estimated? That is the beta naught and the beta 1. Okay, so the way they are estimated, we're actually going to use what we call the method of maximum likelihood. Okay, the maximum likelihood estimation method. Okay, and when I talk about maximum likelihood method, it means we actually want to find the slope and the intercept that maximize the likelihood. Okay, what is likelihood here? That maximize the probability. Okay, so and then for us to do that, and that is the reason why we're actually going to use a GLM in the code. Okay, the GLM in the code is actually uses maximum likelihood estimation to estimate the model coefficient. Okay, it means if you take a look at what I have here that I run in R, the file that I've already put a GLM these estimates here, they are not least square estimates, but they are maximum likelihood estimates. And that is the reason why instead of you to have a t value, you're actually going to have a z value. Okay? Because why do you have a z value? You have a z value because the maximum likelihood estimation actually operates under the assumption of a normal distribution. Okay? Of course, this is more or less like a standardized, z value. Okay, so the next thing that I actually want to talk about now is likelihood versus probability. Okay, let me first give you the definition of probability. Okay, probability is a measure of likelihood occurrence of an event. Okay, we are in a world, we got a lot of variation. Okay, so of course, probability thrives in variation. If there is no variation, we cannot be talking about probability. Okay, we can be talking about probability. Okay, now if you look at the first thing here, I said, although the likelihood sounds like probability, but they are not exactly the same. Okay, if you look at the word likelihood, okay, it's more or less likely. Okay, now, and I said the paraphrase from a helpful post from website Stack Overflow. Okay, define likelihood probability as this. It's a probability quantifies anticipation of the outcome. Okay, when I say quantifies anticipation of the outcome, if I apply for a mortgage loan, okay, I can actually determine the probability that I'm actually going to be granted. So it means if I'm able to do that, I'm actually quantifying the anticipation of the outcome. Okay, but when I talk about likelihood, okay, the likelihood quantifies trust. Okay, and trust in what? Yeah, that is the trust in the model and its parameters. Because if I actually want to determine the probability of whether or not I'm actually going to be granted a mortgage loan, of course, that will be subject to the model parameters. Because I know they're going to look at my credit score, they're going to look at some other predictors. Okay, if I'm able to estimate the parameters in the model, then I will actually be able to obtain the probability value for that. Okay, and that is the reason why we said the likelihood quantifies the trust. It means we actually want to how can we measure the trust in our model and its parameters? We will be able to model the trust. We can be able to quantify the trust in the model and the parameter if the parameters are accurately determined. Okay, when the parameters are accurately determined, because in a situation where the parameters are not accurately determined, of course, there's possibility that we could have a kind of misleading decision at the end of the day. Now, because of that, I'm actually going to introduce a concept right now. Okay, and don't forget that I said when you have a model, the model has a combination of parameters. Okay, every statistical model has combination of parameters. Okay, now take a look at what I have right here. I want to find the reason why I said there's a difference between probability and likelihood is just that let me interpret what this is talking about. So this is like, what is the probability of my data, okay, given the model? But this guy is saying, what is the likelihood of the model given that I've observed the data? Okay, so if you take a look at that, they are not the same. Okay, so which means one is actually going, the direction here is just that, okay, if I want to estimate parameter, I actually need to make use of my data set. Okay, so this is trying to say parameter actually implies the data. Okay, but right here, this is saying data implies parameter. Okay, parameter implies the data is just that, okay, the moment I understand the parameter, then I will be able to make a prediction about the data. Okay, but this guy is actually telling me here is that understanding of the data will enable me to be able to, determine my parameter. Okay, so, and I'm going to put an example right here. If theta equal to 0.7, okay, what is the probability that I get 8 heads in 10 flips? Okay, what is the theta right here? Or maybe the theta here is the probability of getting head. Okay, if the probability of getting head is 0.7, okay, if this is theoretical, okay, if I go into experimental probability where I play with I flip a coin for 10 times, okay, the question is, what is the probability that I'm actually going to get 8 heads? Okay, so here I'm trying to figure out probability, but if you take a look at the likelihood is going to say, okay, if I get 9 heads in 10 flips, okay, if I get 9 heads, okay, in 10 flip, what theta values are likely true? Look at that. Look at that. Can you compare the two? Okay, this is actually talking about likelihood here. What theta values are likely true? So anytime you are trying to say what theta values are likely true, you are actually investigating the likelihood. And that was the reason why I said the likelihood will enable us to quantify trust. And how can we quantify trust? Trust in what? Okay, trust in the model and its parameters. Okay, and that is the reason why we are trying to say that right here. Okay, so because of that, I'm actually going to take you to, if you want to answer the question here on the probability, okay, if you can you guys hear me?
Yes.
Okay, I just want to see whether you guys are really following. Now, if I want to answer a question that has to do with this, okay, the very first thing I need to ask myself, what kind of probability distribution, exhibits what this experiment? When I have a coin, and I'm flipping a coin, okay, of course I'm actually going to have a binary event, okay. It's either I have a head or I got a tail. Because of that, the probability distribution for that is binomial. Okay, yesterday I told you what we call Bernoulli. Okay, Bernoulli is when I have one trial, but binomial is when I have so many trials. Any trial more than one. Okay, a Bernoulli trial. Let me put it this way: when I toss a coin once, okay, it's either I have head or I get a tail. Okay, that's a Bernoulli. But when I toss it so many times, tossing it so many times, okay, it's either I can have a head, I can have a tail, and that becomes a binomial. Okay, so what I want to use right here to figure out this problem is what we call binomial distribution. Okay, in the binomial distribution, we actually going to have n combination x, okay, uh, the probability raised to power x, and 1 minus probability raised to power n minus x, okay, and that is the reason right here you have 10 trial, 10 flips, and the question is, I want to get 8 heads. Okay, it means my y equal to 8. That's what I'm putting right here. Then the probability of getting that, the theta is 0.7. I'm going to raise that to power 8. Then I'm going to do 1 minus 0.7 raised to power 10 minus 8. Okay, and 10 minus 8 equal to 2. So it means the probability when I flip a coin 10 times, okay, when I flip a coin 10 times, the probability of getting 8 heads, okay, given that the theoretical probability of getting head at all is 0.7 is what we compute right here. Okay, so this is a way to compute probability, okay, using binomial probability distribution, judged by the fact that we're talking about a binary variable, okay? But if I want to compute the likelihood, okay, if I want to compute the likelihood, I'm actually, computing the likelihood is just that, want to get what is it, the likelihood of theta given that y equal to 8, okay? The probability that we have here we use is 0.7, okay? The question now is, can we have a way to estimate our parameter, okay? Instead of using this 0.7 here, can we have a way, if I know, okay, if I have information about my response, is there a way I can actually figure out the optimal value of a parameter? Okay, now if I want to do that, I'm actually going to have a, consider some values of parameter. So that was why I said, given potential theta values, we could calculate its likelihood. Okay, suppose the potential theta values are 0.1, 0.5, and 0.9. Okay, let me tell you something. We're actually going to have a parameter space. Okay, and then we believe the parameter within the parameter space, we are actually looking for the optimal values of parameter. Okay, there's always going to be a guess, because when you are doing research, your mind can never be empty. Okay, we're going to have something in mind. Okay, so, and that is why we have the potential values for theta 1, for the theta, which is a 0.1, a 0.5, and a 0.9. Okay, now what we want to do right now is we're going to use this formula again right here, but only that in using this formula, we're going to first test for when theta equal to 0.1. Actually, you can see that now. For when theta equal to 0.5, you can see that now. And for when theta is equal to 0.9, you can see that now. But if you compare the likelihood here and the likelihood here and the likelihood here, the biggest one, the largest one, is the one that we are actually going to consider. Why do we want to consider the largest one? And that was because of the method. The method is called the maximum likelihood. Okay, that was why we call it the maximum likelihood. Okay, because we actually from the possible values of the parameters that we have considered, which one is the largest? Okay, we consider 0.1, 0.5, and 0.9, and at the end of the day, look at the likelihood that we have. Okay, the value of a likelihood is actually going to tell us whether we should trust that parameter or not. Okay, if you take a look at this guy here, this is 0.194, is higher than every one of that. Therefore, among the three potential values, okay, of the theta, okay, theta is most likely to be 0.9. Why is it most likely to be 0.9? Because the likelihood associated with the theta equal to 0.9 is the largest. Okay, is there anyone you want to ask question on this? Is there anyone? Somebody may be telling me that, why do I consider just 0.1, 0.5, 0.9? You can as well consider everything. You can consider 0.1, 0.2, 0.3, 0.4, up to 0.9. Okay, there's no problem. But you know what? We're actually looking for the likelihood that, and let me tell you something, it is not all the time that when the theta value is high, that the likelihood is actually going to be high. Okay, but based on what we are doing right now, okay, we realize that the likelihood that correspond to the theta value of 0.9 is the one that gives the largest value. Is there any question before I move forward? Is there any question? Okay, let us now have a review right now, or the review on the likelihood of a logistic regression. Now that you understand how likelihood is being estimated, what I'm just trying to show you right here is just to be able to show you how likelihood are estimated, and then how we always want to declare for the parameter that correspond to the largest likelihood. Okay, now we want to use that idea now to estimate parameters in a logistic regression model. Okay, in a logistic regression model, this is a logistic regression model. Okay, this is a logistic regression model. Okay, you know, of course, you know, this guy here is a y cap. Okay, which is a probability, the expected probability of the characteristics of interest. Okay, now before I can use this model, I need to use the method of maximum likelihood to estimate the parameter beta naught and the beta 1. Okay, so we want to use the maximum likelihood approach for that. Okay, now let me tell you this: the parameters in this model are beta naught and beta 1. Can you guys hear me?
Yes.
Okay, I'm just trying to be sure. Now, the parameters in this model are beta naught and beta 1. Okay, now it means the likelihood that I want to get now, I'm seeking the largest likelihood for the combination of these two parameters given the values of my response. Okay, given, you know, this is a value of response across the sample size of individuals in my cohort. Okay, now I'll take a look at this. What I want to show you right now is just a manual way to do that. But of course, in R, I've shown you the other time, you know, the moment you put a GLM, you write the code in R, you're actually going to get your results. Okay. But I just want to walk you through the manual way to figure that out. Okay. Now, let us work on this data set. Okay. This is the response is categorical. Okay. And this is a predictor. Okay. Now, what I want to do right now, if you take a look at what I have right here, okay, I'm actually starting with a beta naught equal to 0 and beta 1 equal to 0.5. Okay, you know, I told you the other time that uh, we actually want to investigate, okay, different values of parameters. Okay, now, uh, you know, I got from y1 up to y5, which is just talking about the response, okay, that I got right here. Okay, now if you look at this guy now, is trying to talk about the probability of y1 equal to 1, y2 equal to 1. I'm talking about this up to y5 equal to 0. Okay, given these two parameters, okay, given that the beta naught equal to be equal to 0 and the beta 1 is equal to will be equal to 0.5, do you know that if I'm seeking the likelihood, I can rewrite this as the product of the respective response given the likelihood. Now this is given the parameters. This is what I'm trying to say. If this is a joint, what I have here is a joint. Why is it a joint? I got all the responses from y1 to y5, given the values of the parameters. And I'm actually going to, what I'm trying to tell you right now is that this can be partitioned into 5. Okay, look at the first one, into the probability of y1 equal to 1, given the parameter, the probability of y2 equal to 1, given the parameter, until I get to the probability of y equal to 0, given the parameter. Can you see that now? So this, what I have right here is more or less what I partition into 5 different components. Okay. Now, let me tell you, based on this first component, based on this, based on the first component right here, I can actually write a logistic regression for that. On this one, I can write a logistic regression model for that, and so on like that. Look at that. So that is why it means this is the logistic regression model for the first probability, okay, for this one, then logistic regression model for the second one, and so on until I get to the last one, okay? So, and when I do that, okay, it means working on this one right now, okay, when I plug in the value on this, what am I plugging? When I put 0 here and I put 0.5 on the beta 1, okay, and then if you look at the x1 here, when I plug in 5, okay, look at that, that's why I plug in 5. Now, this guy here is, I'm going to get a 0.92. Okay, I'm going to do it to the same to the second component. In the second component, I'm still using a 0 and a 0.5 in my parameter, but what I'm going to be plugging in on the x2 is actually going to be 7. Okay, look at that. When I plug in that and I compute that, that will give me 0.97. Okay, I'm going to continue to do that until I get to the last one. Okay, I'm going to continue to do that until I get to the last one. But there's something I need to tell you. When you get to the last one, if you take a look at what I have right here and what I have right here, is when I'm considering when y equal to 1, 1, and 1. Okay, because when you get to a situation where there is 0, okay, where the response is 0, it is expected that you do 1 minus that. Okay, so you're actually going to do so. Now if you take a look at what I have right now, if you multiply the probability that you compute all together, the probability will be 0. You're actually going to have a 0.19. Okay, now if you have a 0.19, what are we actually talking about with the 0.19? The 0, we said something the other time that the likelihood, okay, the likelihood of that can be expressed as this, and which was, so it means the way we can trust that particular model, okay, the likelihood that we obtain from quantifying the likelihood from that particular model, of course, we're actually going to have a 0.19. Okay, another thing I'm going to talk about is the deviance. Okay, and then why do I need deviance? Okay, if I want to determine if after fitting a logistic regression model, okay, and how do I test for the model fitness? Okay, in the linear regression model, we use residual sum of square. I think you remember that. Okay, because the least square that we actually use in estimating parameters in the linear regression model, we ensure that the residual sum of square is going to be very, very small. Okay, but in a logistic regression model, the models are not fitted by least square. The models are fitted by maximum likelihood. And if the model are fitted by maximum likelihood, then we're actually going to use deviance to measure the model fitness. Okay, this can come out in a multiple choice in the final. Okay, where I can actually ask you to, where to, like, when I'm fitting a logistic regression model, and then what is a measure, what do we use to estimate parameters in a logistic regression model? What approach? I need you to tell me maximum likelihood approach. But for the case of linear regression, I need you to tell me least square. Okay, and then of course, if I ask you about what we use to measure the fitness of a logistic regression model, I need you to tell me deviance. Okay, the deviance is the same thing as a residual. Okay, and you know what? How do I compute my deviance? If I want to compute my deviance, it's actually going to be g squared. The symbolic representation of the deviance is g squared. Please don't write a lowercase letter. You need to write an uppercase letter, and it is equal to -2 times summation the yi log yi cap plus 1 minus yi log 1 minus yi cap. Okay, and the better fit, okay, the model with a better fit is the one that have a larger likelihood or log likelihood. Okay, and then a better fit also imply smaller residual or smaller deviance. You remember in when we're dealing with the linear regression model, when you are using the p-value, of course, the when you have a p, if a p-value is small, it means the test statistics is large. Okay, so what I'm trying to talk about right now, when you want to base your decision on the likelihood or on the log likelihood, you need to consider the larger one. But if you want to base your decision on the residual, or that we call the deviance, then it has to be a smaller deviance. So I'm actually going to walk you through how you can actually compute this. And there's something that we call saturated model. Okay. In saturated model, we're actually going to look at the number of model parameter, because the number of model parameter has to be equal to the sample size. That's what we call saturated model. I'm actually going to explain that to you. Okay. Uh, if the number of parameters in the model, okay, the beta naught, the beta 1, and so on like that, if it is the same thing as the sample size, that's a saturated model. Okay. And we can have a situation whereby the number of model parameters, if the number of model parameters is greater than the number of sample size, that can be an issue. Okay. That can really be an issue, a very real issue. Okay. So most of the time, we want a situation whereby it's either the model parameters are equal with the number of experimental units, or we even want number of experimental units, that is, the sample size has to be strictly greater than the number of model parameters. Otherwise, the degree of freedom is actually, it's not going to be fine. But let me tell you something. When I say saturated model, if the sample size and the number of model parameters are the same, I may not be able to find the degree of freedom, because the degree of freedom is going to be n minus k. Okay, in that situation, n minus k will be equal to 0. Okay, so I'm going to walk you through that as time goes on. Okay, so this is a deviance for model M. So this is a formula, and let me tell you something. uh, in this formula is just going to tell you that the log of saturated model minus the log of the model. Okay, the log of saturated model minus so let me tell you something. When you want to do that, we're actually going to have an hypothesis. Okay, we're going to have an hypothesis, and I'm actually going to walk you through that. And you know what? Is g squared less than 0? The g squared cannot, we call something squared. The fact that we call it squared, okay, it means it's not going to be equal to 0. So it's actually going to be positive. Okay, I'm still going to walk you through that. The next thing I want to talk about is, how do we compare two logistic regression models? The other time, is in the linear regression model, I taught you how you can compare models, okay? In a logistic regression model, how do we also compare between two logistic regression model? You remember the other time, we in the linear regression model, we compare intercept model with another model. We also compare a complicated model with a simpler model. Okay, that is in the framework of a linear regression model. Also, of course, what we were using in doing that. In one, we're computing the F test. In the other one, we were actually conducting partial F test. Okay, I think you remember that. But you know what? The way we do that in logistic regression is quite different from the way it is done in a linear regression. Okay, and I'm actually going to start with the two models right now. Where in the null hypothesis, we got a simple model, and in the alternative hypothesis, we got a complicated model. Okay, and let me tell you this, if I really want to compare, we're going to make use of a chi-square test. And you know what? The chi-square test is actually going to be the difference of the g squared. Okay, and I showed you g squared here the other time. Look at the g squared. Okay, it means I'm actually going to have 2g squared. Why am I having 2g squared? Because I'm going to have, this is a g squared that has to do with a simple model, and this is a g squared that has to do with a complicated model. Okay, the test statistic is just to find the difference between the the g squared for the simple model and the complicated model. Okay, don't forget that we're actually going to be comparing the simple model with a complicated model. Okay, and you know what? This test statistic actually follow a chi-square distribution. Okay, if I want to get a critical value, okay, I'm actually going to be using the chi-square distribution, and you know what? The K here would be the degree of freedom. Okay, and right here I show you, this is like the shape of a chi-square distribution at different degree of freedom. okay? Because the shape of it depends on the degree of freedom, okay? Uh, Now, let us have a practical demonstration of what we have been doing, okay? We want to have a practical demonstration of what we have been doing, okay? What I'm showing you right now, we have two logistic regression models that are competing, okay? One is a simple model, and the other one is a complicated model, okay? And we actually want to decide on which model is better, okay? Which model we are actually going to prefer, okay? If you take a look at what I have right here, the outcome here is actually based on age, okay? The age is the only predictor in this model right here. You remember the other time, we are still using the data set on the, uh, the outcome variable is actually going to be alive or dead, okay? So right here we are looking at the effect of age, okay? We are looking at the effect of age on the outcome, and the outcome is alive or dead, okay? That's what we're trying to look at in this model. But in the second model, we are looking at the effect of age, effect of smoker, and effect of the interaction between age and smoker. You remember that we did an interaction model the other time in linear regression. We can also talk about interaction in a logistic regression, okay? So this is the second model right here is an interaction model, okay? Because this will enable you to estimate the contribution of the main effect, okay, the age and the smoker, and it's also going to enable you to estimate the contribution of the interaction effect, okay? So the logistic regression model for this is this, and the logistic regression model for this is this. Is there anyone who have a trouble time understanding the way these are set up? Is there anyone? Is there anyone? Can you guys hear me?
Yes.
Yes.
Okay, so these are the two competing logistic regression model. The fact remain is that if you look at what model one is trying to talk about, the one I call the simpler model is trying to look at the effect of age on mortality. Okay, looking at the effect of age on mortality is just like looking at the effect of age on where on the dead, or whether somebody is going to be dead or is going to be alive. Okay, but right here we are looking at the effect of both age and the smoking and the interaction on this, okay? And that is why, and right here under the null hypothesis, you're actually going to have the simpler model. Why is it simpler model? Because it contains few number of regressors, okay? Here, how many regressors do I have? 1, 2. How many regressors do I have? 1, 2, 3, 4, okay? Now, this is the graph. So it means what we are actually testing under the null hypothesis, this is the same thing as model 1. Okay, it is the same thing as model 1 because if beta 2 equal to 0, okay, if beta 2 equal to 0 and beta 3 equal to 0, of course, you're going to go from here to here. Okay, so beta 2 and the beta 3 are the one that are explaining the contribution of the smoker years and the interaction. Okay, and that is the reason why that is what you have under the null hypothesis. So this is more or less the same as model 1, and why this is the same as model 2. Okay, and if that is the case right now, we actually need to go into R, to write a code. Okay, take a look at that. This is the code for model 1. Okay, this is the code for model 2. Okay, and you remember what we did the other time when we are comparing models in linear regression. You remember that we're going to write ANOVA into the two model, but in the case of logistic, we have to include test equal to psych. The moment you include test equal to psych, of course, is actually telling you that this is a way to compare two models, two logistic regression model. Okay, so you have to indicate this. Okay, now this is the result. This is the output. The output is going to come out this way. It's going to be called analysis of deviance. Okay, analysis of deviance. I think you remember the other time that we talked about deviance. Okay, so the arrow will automatically compute the deviance for you. Okay, and it's actually going to compute the deviance of the two model. Okay, it's actually going to compute the deviance of the two model. It's going to compute the difference of the deviance. Okay, so what you're going to see right here now, take a look at what I have. This is model 1 and this is model 2. Okay, and this is a table. Okay, now this is what you're going to check for. This is the deviance that we talk about, and this is the p-value associated with the deviance. Okay, if you want to take a decision regarding model 1 and model 2, you're actually going to focus on the p-value. Okay, so what can you see right here? The p-value is larger than 0.05 level of significance. Okay, and when the p-value is larger than a 0.05 level of significance, it means we're going to fail to reject the non-hypothesis. Okay, failing to reject the non-hypothesis right here, it means we are actually going to settle for model 1, which is the simple model. Okay, and that was why I said we fail to reject the non-hypothesis, the simple model, which means traditional regressors, smoker and age. Okay, smoker do not significantly improve model fitness. Okay, and that actually justify what one of my students, what one of you said the other time about the 91-year-old guy, you know, that died. He was a smoker, but the fact remains that it may not be smoking that contributes to his death. It could be old age. Okay, and you can actually see that right here. Okay, and that is why. So this is actually supporting the fact that smoker do not significantly improve the model fitness. Okay, so we will want to select the simple model. Okay, it means as far as mortality is concerned, based on what we have investigated right now, this age is the major potential factor. Okay, so another way to obtain the test statistic value and the p-value is actually to put a summary on M1. And what is my M1? I'm going to show you right now. This is M1. Okay, the M1 is talking about the simpler model. Okay, the M1 is talking about simple model. Now, if you take a look at the simple model right here, and you look at the age, you can see that age is highly significant. You can see that now. Age is highly significant to it's a significant predictor to either being alive or dead. Okay, and then if you look at the AIC, I told you the other time, if we have computing models, of course, you can compare models by AIC. Okay, I think you remember that. You can compare model by BIC. We can compare model by adjusted R-square. You remember that we talk about model selection criteria. Okay, so what I'm trying to tell you right here is that when I run a simple model, okay, the AIC for the simple model is this. Okay, I think you can see that now. So the summary of the simple model, okay, is this. The summary of the complicated model is this. Now let us compare the two model by AIC. Okay, let's compare the two model by AIC. Okay, as you can see right here, you're going to see that model 1 has a smaller AIC. Can you see that now? So by using AIC, model 1 is preferable. Okay, and you can see again that if you take a look at what we did right here, the p-value here also suggested that model 1 is good. Okay, so it's either you make use of that or you also make use of the p-value. Okay, of the AIC. Okay, look at the AIC of the first model, look at the AIC of this second model, and the AIC of the first model is smaller than the AIC of the second model, and that actually justify that the first model is better. Okay, another thing you can check if you take a look at residual deviance here. Okay, the residual deviance here is actually greater than the residual deviance here. But the most important is when you look at the AIC. Okay, AIC is more superior. Okay, right here we are trying to tell you the degree of freedom associated with the model 1, and this is the degree of freedom associated with that. Okay, now based on what you see right here, okay, do you know that we can actually compute the test statistic? Okay, and the test statistic is going to be the difference between the two deviance. Okay, I can take the deviance right here and the deviance right here. Can you see that now? And I subtract them. Okay, I'm trying to tell you the deviance that I talk about is the residual deviance. Okay, this is the residual deviance of the first model. This is the residual deviance of the second model. This is what I call the G square that I talked about the other time. Okay, in case you actually want to extract the G square in our output, okay, from our output, okay, so the difference between that give us 3.83, okay, and the degree of freedom of the test statistic under the H naught, okay, under the H naught, I'm actually going to subtract the degree of freedom for this residual minus the degree of freedom for this residual, and that is actually going to be 2. And if that is a 2, that is what I'm going to check for in the chi-square table. So it means in the chi-square table, the degree of freedom is equal to 2. So this is the code. Okay, I'm going to put the deviance right here under the degree of freedom 2, and this is the chi-square. Okay, so what do I have here? I got a 0.14734. Okay, now let me take you back. You can see it's the same as what we have here, right? So you can see that now. It's more or less it's the same as what we have right here. I'm just trying to show you another way you can. So you can see at the end of the day, you still have this. And of course, the p-value here is larger than 0.05 level of significance. Okay, because it is larger than 0.05 level of significance, of course, we're going to fail to reject the non hypothesis and conclude in favor of model 1. Okay, we're in favor of the model that talk about only age as a predictor to the outcome of whether somebody is going to die, somebody is going to be alive or not. Okay, so what I'm trying to show you right here is just the density curve of the chi-square at the degree of freedom 2. Okay, the 3.83 is actually you can see the 3.83 right here, and the probability value associated with that is what we just computed. Is there anyone who have a question to ask, as this is going to be the end of my lecture today? Is there anybody who want to ask question? Somebody said, what does Z value mean? Of course, the Z value mean, of course, I told you the other time that the output under the logistic regression, you are not going to see a T. What you are going to see is a Z value. Okay, the Z value that we're talking about, we are more or less talking about normal distribution. Okay, if you have heard about Z test and a T test. Okay, this is more or less like a Z test. Okay, under logistic, testing the significance of the parameter there is actually going to be a Z test and not a T test. Okay, we have a T distribution and we have a normal distribution, and we got a T test and we got a Z test. Have I answered your question now? Okay. Okay, so is there anyone who want to ask question? Is there anyone who want to ask question? Is there anyone? I want to thank everyone today for attending my lecture, and I want to also appreciate you guys, for despite the fact that I got challenges uh, about the frustrations in the internet, you see kept by